Okay, so let us consider in general an n cross n matrix of this form. Okay, this matrix is n cross n. It's upper triangular. It's got zeros along the diagonal. Okay, zeros along the diagonal, and it's got ones on the super diagonal. Okay, so this is all ones, and so it's ones on the super diagonal, zeros on the diagonal, and zeros everywhere else. Okay, so that's the structure. So 3 cross 3 matrix we already wrote before. We can similarly construct 4 cross 4, 5 cross 5, and so on. Right? Any number of matrices. Okay. So let us look at some simple properties of this matrix. Okay. So one property that I already told you is very crucial for everything else is that when you multiply m with x, right, that is x1 x2 to xn, what it will do is it will push up the coordinates. Okay, meaning that the last coordinate will be pushed to the previous and so on. First coordinate will be thrown out, and in the ending you will get a 0. Okay, so xn minus 1, xn minus 2, so on up to x2. Okay, x1 entry is thrown out. Sorry, made a mistake here. xn minus 1. Okay, that's how you get it, right? So in the case for 3 cross 3, we had the action given as x2 x3 0. Okay, that was n equal to 3. Okay, so you can see that fits with this. So this is what this matrix does. When it multiplies a vector, it sort of cyclically shifts, as I mentioned before. Okay, using this you can immediately say that the only eigenvector of m is E1. Okay, and the only eigenvalue is 0. Okay, the characteristic polynomial of m is lambda to the n. Okay, by the way, for characteristic polynomial, from here on let's use mu as a variable instead of lambda. Okay, reasons I'll mention later. Basically I want to do det of mu I minus a. So mu is my variable for the characteristic polynomial. Instead of saying lambda, I'll say mu. Okay, just for sake of simplicity and consistency in some notation. Okay, so det of mu I minus a, the characteristic polynomial in this case is just going to be mu to the n. It's very simple, right? We already saw this for the 2 cross 2 case. We got mu square, and 3 cross 2 was mu cube, right? Okay, so this is also very easy to see. So this is the diagonal, this is the super diagonal. Okay, zeros, upper triangular matrix is ones on the super diagonal, everywhere else is 0. Okay, fantastic. So these properties can be readily seen. So to verify this, I'll again leave it as an exercise. We've already done it. There's no point in repeating it. We did it for 2 cross 2, 3 cross 3. It's the same thing here, right? So characteristic polynomial is mu to the n, so you know that 0 is the only eigenvalue. And when you try to find the eigenvectors, you can simply equate this to all 0 vectors. So that makes x2, x3 up to xn, all of them 0. x1 is the only free coordinate. Okay, so you only get multiples of E1. Okay. Very good. So these are the two main properties. So it's very interesting to see that this is an n cross n matrix with only one eigenvector. Okay, fine. So it's like really the eigenspace is really small. The set of eigenvectors is much smaller compared to the overall input and output spaces. Okay, fine. Let us see some other sort of very interesting consequences. In particular, let us see what happens when you apply m twice, right? So that's arising naturally here, because what this m is doing like a one step shift, right? It's shifting xn up, xn minus 1 up, like in one step. What if you do this process again, right? So what happens when you do m square? Okay, what happens when you write m square, right? So it's very easy to understand from the action m square x1 x2 to xn, right? That's going to be the first step. I'm going to shift them up, so I'm going to get this. In the second step, I'm going to do this shift on this vector. Okay, so 0 is going to be pushed here, okay, and it's going to be pushed up and so on. So x2 is going to be thrown out, and you're going to be left with x3, x4, so on up to xn, and there are going to be 2 zeros at the bottom. Okay, something like this. So this is going to be the action of m square. Is that okay? correct? So please recall that m e1 is 0. Why is m e1 0? Because e1 is an eigenvector of m, right? M square here is going to be a vector that has one additional 0. So m has like 1 0 here that you introduced apart from the coordinates. M square has 2 zeros. Okay. So what would be, for example, m square e2, if I may ask? M square e2 will be what? Will be 0, right? Because what happens is, when you do m square, you're throwing the top two coordinates out, right? The top two coordinates have been thrown out, right? So when you apply it to e2, remember e2 is a vector that has got like, something like this, right? It's got 0 1 0 0 0. That's the vector e2, correct? So when you apply m square to e2, the top two coordinates, these ones will be thrown out, but everything else is 0, right? So we'll get m square e2 equal to 0. Okay. So what is very interesting here is that m zeros out e1, right? This is one way to interpret it. M zeros out e1, m square zeros out e2. Okay. In fact, m square zeros out both e1 and e2. Okay, zeros out both e1 and e2. Okay. So what you can see here is that if you look at the null space of m, the null space of m is going to be just the span of e1, correct? Because the only vector in the null space of m is e1. The only unit vector in the null space of m is e1, right? Because any vector in the null space is an eigenvector of eigenvalue 0, right? And you know that there is only one eigenvector. Okay. Similarly, one can say that the null space of m square is actually the span of e1, e2. Okay. And you can actually generalize this. You can say null space of m cube equal to span of e1, e2, e3. Okay, there is a nice sort of a very tiered structure to this, right? So what is happening is when you do m cube, right, the top three coordinates will be thrown out because of the way the shift operation works, right? The top three coordinates will be thrown out. But when you do e3, e1, e2, e3, everything that's non-zero is present only in the top three coordinates, right? Everything else is 0, correct? So null space of m cube will be span of e1, e2, e3, right? So we can keep continuing like this. Can someone tell me what will be the null space of m to the n? It will be the span of everything e1, e2 to en, but that's just going to be the whole space Rn, correct? Because when you do m to the n, right, m to the n, you're going to throw out the top n coordinates, right? In m you throw out the top coordinate, m square you throw out the top 2, m cube the top 3, m to the n the top n, all of them are gone, right? So null of m to the n is Rn. What that means is basically m to the n multiplied with any vector will give you 0. Doesn't matter what the vector x is. Any vector will give you 0, right? In other words, m to the n itself is going to be the 0 vector. 0 matrix, right? M to the n is just going to be the all 0 matrix. Okay? All 0 matrix. Okay? This property sometimes is also written slightly differently. Basically, whatever we discussed here, so this third property is something new that I'm adding compared to the previous part. It's also written slightly differently. If you actually see, you have m times e2, right? What is going to be m times e2 is going to be e1, correct? Because when you do this shift operation, right, when you apply it to m, let's look at this definition here. When you have e1 here on the left side, when you have e2 here on the left side, then basically by shifting, you can see that on the right side you end up with e1, right? M of e2 equal to e1 and m of e1 is equal to 0. Okay, and similarly you can write m of e3 is equal to e2. Okay, so in general you can write m of en is equal to en minus 1, m of en minus 1 equal to en minus 2, so on. M of e2 equal to m of e2 equal to e1 and m of e1 equal to 0. Okay, so in some sense what is happening here, this is basically the shift operation, right? It's basically the shifting that is going on in this matrix, right? So we can see that sometimes what people write is like this. They draw a chain like this. And you see that whenever you apply m to any element of the chain, you end up one step in the next to the right. Okay, so let's say you do m of en, you get en minus 1. If you do m of en minus 1, you get en minus 2. Okay, that's basically the shift operation in action, and ultimately m of e2 will give you e1. Okay, and when you do m of e1, you will get 0. Okay, so this is called a chain. Sometimes it's called a Jordan chain. Okay, the reasons we'll see. It's called a Jordan chain because it in some sense describes the action of this m, right? Okay, fine. So this is basically what it is. It's actually extremely simple if you understand this idea. Okay, what m does to any vector, it actually shifts it up. Okay, fine. We're going to see that arbitrary matrices also are going to act this way in some sense. Okay, that's what's going to be very surprising about it. Not just this particular matrix that we have drawn here, right? Okay, fine. Okay, so these are the main properties that I wanted to discuss about this matrix. Okay, now let us generalize our matrix slightly. Okay, so what I'm going to do is the same matrix as before, but instead of picking 5, right? So 3, 4, 5. Let me just try to be systematic so I can write it properly. Instead of picking zeros in the diagonal, let me pick some constant lambda on the diagonal. Okay, so it's a 5 cross 5 matrix I'm drawing here as an example. 5 cross 5 matrix I'm writing here as an example. So diagonal entries are lambda. It's still upper triangular, so everything below is 0, right? And there are ones on the super diagonal. Okay, and everything else is up here. Okay, so it's the same as before, except that the diagonal entries are made to lambda. All the same, right? Instead of making them 0. Okay, this we're going to denote by j sub n lambda. Okay, the subscript n denotes the size. This is an n cross n matrix. Okay, the subscript n denotes the size. Lambda denotes whatever scalar is present on the diagonal. Okay, and ones are on the super diagonal and everything else is 0. This is called a Jordan block. Let's try to understand if similar properties happen for a Jordan block also. Okay, that's what I'm going to discuss. Is that clear to everybody? Right? Okay. So one thing to realize is if I take Jn of lambda minus lambda times identity. Okay. So basically here the only difference in this matrix compared to the one we considered previously is that you have some scalars lambda on the diagonal. That's additional. Okay. So what if I get rid of them, right? So Jn lambda minus lambda I is a matrix of the form discussed before. Okay. So it's a matrix of the form discussed before. Okay. So most of what I'm going to say is going to follow from this intuition. Okay. Fine. So let us look at some very interesting and simple properties. So what about the action of Jn? So instead of looking at the action of Jn, I'm going to look at the action of Jn minus lambda I. Okay, the action of Jn minus lambda I on a vector x1, x2 to xn is going to be the shifting action. Okay, so it's going to shift xn, xn minus 1, so on, x2, the first coordinate will be thrown out and the last coordinate will be made to 0. Okay, so that's what is the action of Jn minus lambda I. Again, same as before, right? Nothing really different, correct? What is the characteristic polynomial of Jn, right? So if you do the characteristic polynomial of Jn, we have to do det of mu I minus Jn lambda. That's the definition, right? Now you know I wanted to pick mu instead of lambda here because I didn't want you to confuse the two lambdas, right? So det of mu I minus Jn lambda, if you compute, you will get mu minus lambda whole to the n. This will be the polynomial. So remember, this is a function of mu, right? As far as our thing is concerned, lambda is some fixed scalar that I am putting here on the diagonal. Okay, it's mu minus lambda to the n. So lambda is the only eigenvalue. Okay, lambda is the only eigenvalue. Okay, with multiplicity n. Okay, that is with multiplicity sorry, n, yeah, with multiplicity n. Okay, so this is going to be the algebraic multiplicity. This is going to be the algebraic multiplicity. Okay, fine. So that is the characteristic polynomial. What about the eigenvectors? Right. Once again, the only eigenvector is E1. Okay, with eigenvalue lambda. Okay, because after all, what you have to do, right? If you have to find an eigenvector corresponding to lambda, you have to look at a vector in the null space of this, right? We've already done this. E1 is the only vector in the null space of this, right? So E1 with eigenvalue lambda. Okay, fine. So that is another very important property. So this is an example of another n cross n matrix with eigenvector E1. Okay, but the eigenvalue is lambda. Okay, fine. And then similarly, you can say Jn lambda minus lambda I whole square. Okay, so this, the null space of this is the span of E1, E2. Okay, similarly, the null space of Jn lambda minus lambda I whole cube is span of E1, E2, E3. Okay, so on and so forth, right? So in general, continuing in a similar argument as before, Jn lambda minus lambda I, this matrix, when you take it to the power of n, you're going to get 0, right? Where n is the size of this matrix. Okay, it's the same n here, right? When you get you will get 0. It will be the 0 matrix. Okay, again you will get a similar chain sort of structure. So En minus 1, En minus 2, so on, E1, 0, right? So if you apply this map, Jn lambda minus lambda I to En, you will get En minus 1, right? If you apply Jn lambda minus lambda I to En minus 1, you get En minus 2. Okay, because this whole thing is just a shifting operator, right? So nothing really has changed here, right? So this is basically what the Jordan block is. Okay, fine. So with all of this in mind, we're going to discuss Jordan decomposition next.